I still have a few more exams to hand out, so if I didn't get yours, it's just timing in the morning. Come by and grab me right after class, and I'll hand them back to you. I also emailed individuals who didn't complete certain parts of it that I need in order to complete the exam wrapper, so I gave you some feedback. So please make sure to check your email. Also, I probably spent way more time than I should have going through these exam wrappers. I've read everything that you wrote. And so please read everything that I wrote, because I spent probably 12 hours going through these exam wrappers. So I would greatly appreciate it if you looked at the feedback. If you didn't earn all the points back that you could have, I want you to try to use office hours. Some of the stuff, especially the stuff about conversion factors, is really going to become a foundational skill that we need for the rest of the semester. So if you don't get up on that now, it's going to come back and bite you for exam 3 and the final exam, and all of Gen Chem 2. So please make sure to try to utilize study groups, use office hours, whatever you can. Make sure that you can explain in sentences what's going on. And starting next week, we're going to do a lot of explaining of conversion factors using sentences to describe. We're actually going to start on Friday on that. I also had a request to have people that are interested in study groups. To kind of have a sign up. And so what we're going to do is, after class, as you come through, please just put your name on here if you're interested in forming a study group with other people in the class. That way I will send an email to all the individuals here and say, please self-assemble study groups. You can do that based on schedule and all that kind of stuff. But hopefully one of the things I saw is as people were filling out the back of the exam wrapper, it asks you what tools you use and what tools you think you can use in order to improve your capabilities, to get closer, to your capabilities, to make that show on the next exam. And a lot of people, chalk is terrible. Not other things that could be inhaling. A lot of people said study groups is something they want to utilize more. So that's a really, really strong way to see what you know, to try to make sure you can explain to someone else so they can explain it to you. You can find if they're in agreement. So please try to make sure that if you want to join a study group, don't have one currently, or don't have one that you feel is as effective as it could be, come put your name here, I'll email you, and we'll work on putting that together. Exam wrappers, if I have finished your exam wrapper, I posted the scores before class. If I emailed you saying I need something else, I have not posted your score because I need that reflective component of it. Okay. Long question here, very wordy question. This originally was an exam question. I decided that I don't want you guys having to read this much text because this is a lot of the background. So I want you to read it now. I want you to think about water solubility as it relates to metabolism. And then I want you to be able to answer the question at the end of it. So go ahead. We had a couple people kind of walk in late. Go ahead and make sure you've read this question. Once you've read it, talk to the people beside you. How would you decide which one of these would be most water soluble, requiring the least metabolism before being able to be urinated from the body?
In this context, I think it would be
Class is not in agreement here. Okay, so the big take home I want you to think about is that as a medicinal chemist, someone who studied how to influence disease by making small molecules, so as a synthetic organic chemist, I learned how to make these or to modify this one to become this one, that kind of stuff. That's what you'll learn in organic chemistry next year. So if you do a PhD in this, you actually end up making drugs that you end up testing in animals, and then if those are successful, they go to human models, and if they're successful in humans, then they go to mass market. But one of the things that's a real big struggle in medicinal chemistry is if the drug is not soluble, then one, it won't get into your system in the first place. Or if it is soluble, then the question is, what does our body do with it? So a lot of times to get rid of a drug, our body has to make it more water soluble. It chops it up in pieces, and if those pieces are water soluble, it helps our body excrete them. So can I have someone take a stab at which one of these two would you expect to be more water soluble and easier for our bodies to get rid of? You using your one for today?
Yes.
Okay, go for it. Nice and concise. please.
I'm going to go with B, because if you take a look at these two molecules, they are exactly the same, with one difference.
What's the difference?
The difference is that there's a hydroxyl group on one of the carbons right in the middle of that ring. Right.
So what does that mean about water solubility?
That means that that hydroxyl group gives the molecule polarity in more places, and that allows it to dissolve easier in water.
Great. So one of the things we ended last class on was it's not about how many polar bonds we have in a molecule that influences water solubility. What is it beyond that? It's not the number of polar bonds. It's more specific. Love?
It's not how they cancel out each other. And like
Cancel out might not be exactly the term I'm looking for. What's that?
how they arrange each other as a molecule.
It's how they're arranged as a molecule, but a huge part of it's the ratio. And so this molecule, these two molecules, hydrocodone and oxycodone, which I've taken both of these plenty of times for surgeries and other kinds of things. So thinking about what the structure is and why one might be more effective than the other, and no, they weren't illegal. Like how Sam was the only one who couldn't hide our laughter on that. So the only difference is one is slightly more water soluble and it interacts with different proteins because of the three-dimensional shape of it. So that means that instead of having a hydrogen where there's three lines connecting, right, there's a carbon in the middle, there's three lines going out from it, that carbon only has three bonds. So in the structure on the left, there's a hydrogen implied. And the structure in the right, instead, there's an oxygen connected to that carbon. So what I want us thinking about when we're looking at these molecules is how many carbons are there? How many hydrogens are there? How many lone pairs are there? What is the molecular geometry around each one? What's the hybridization around each one? All these different questions you can ask. So if I gave you these molecules, ask yourself, could you determine how many carbons, how many hydrogens, how many lone pairs? What the steric number is? Electron pair geometry, AXE, molecular shape around every single atom. That's what I'm asking you to do next Monday. All right. So I agree with Jackson's summation that that molecule on the right would be more water soluble because it has an OH instead of just an H. So let's go ahead then and let's look back at Abilify. Let's go around and pick out individual atoms. I don't think I put the structure on today's worksheet. Oh, it's on the back page. You should be pretty comfortable with Abilify by now. The structure of it. All right, so go ahead, look at that atom that has the arrow pointing at it. All right, a couple more seconds. Let's go through the steps. Talk to your neighbor about the steps you use in order to get there. Try to do it quickly, about 45 seconds, and then we'll talk through it in class. What steps do we use to decide how to answer this question? Okay, I'd like to hear from some of the groups that are typically quieter in here. Can I hear what our first step is to determine whether there's a net dipole or not? Go ahead, Aaron. Okay, so before we even get that far, I think there's an implication in what you're saying. What do we absolutely need to draw before we answer this question? There's a hydrogen atom missing. Did you guys catch that? How many bonds does carbon always have? 4. Doesn't matter what the steric number is. At some point, carbon is always going to have, at every point, carbon is always going to have 4 bonds. So remember where the line changes directions is the carbon. Right now, there's 2 bonds drawn to the left, 1 bond drawn down. That means that we only show 3 bonds to carbon. That means it's implied there's 1 more bond, and the implied bond will always be to hydrogen. You'll never imply a bond to oxygen or nitrogen or anything else. It will only be implied that we have a bond to hydrogen. So that means that to really answer this question, it's going to be a little crooked here. We have to draw a hydrogen there. All right. What's the second step? Eric. Great. Are there any polar bonds around that atom? Thumbs up, yes. Thumbs down, no. Why are you saying no, Angel? Okay, how do we determine if there's any polar bonds?
Electronegativity.
So we look at the difference in electronegativity between the atoms. Okay, so there's a carbon bonded to carbon. Any difference in electronegativity? Carbon bonded to carbon, any difference?
No.
Carbon bonded to hydrogen, is there a difference?
Yes.
Small. That was why last class I said there's some you're always going to bin as nonpolar. Carbon hydrogen is one of those you're always going to bin in the nonpolar covalent range. So whenever we see a CH, think about oil. Oil that you use to put in your car, or that olive oil. A lot of different oils, they have a carbon tail. They have a long chain of carbon. And that long chain of carbon is a lot of carbons and hydrogens. That's it. Does it dissolve in water? No. Okay, olive oil does a little bit, but that's because it has a polar head group on it. So olive oil actually has this at the end of it.
But olive oil does. Motor oil doesn't.
Yeah, so motor oil doesn't dissolve. You always see it floating on top of water. Those are all carbons and hydrogens. Those carbons and hydrogens are not polar. We consider them nonpolar because it makes it less and less water soluble the more of those we have. Okay? So make sure that you categorize C and H as nonpolar. So then can we answer this question? Do we need to do anything else? Do we need the electron pair geometry, steric number, molecular shape? We don't need any of that. There's no polar bonds. There's no way that our sum of vectors is going to be anything besides nonpolar. Yes, Josh?
Do multiple bonds ever affect this?
So if you have a carbon-oxygen bond that's shorter, double bond, versus a carbon-oxygen bond that's longer, there will be a slight difference in the dipole moment. For this class, we say they're the same.
Okay.
Yeah, Kiana?
So if there's no polar bonds, there's no dipoles?
Correct. There's no dipole for the individual bonds. There's no way they add up to anything besides 0. All right, ready to do a couple more? Aaron?
So we consider it be a zero-sum dipole even if there is a slight difference?
Yes. If we categorize that difference as falling in the nonpolar region, then we just say it's nonpolar.
So,
That difference is so small that we consider it in the nonpolar region.
so we wouldn't say that no, it's not polar, but there is a non-zero-sum dipole.
So for today, I'm talking about zero-sum dipole and non-zero-sum dipole. The translation of that is polar and non-polar is the more general way of speaking about that, but I wanted to have us focusing on the dipole at first before we use the general terminology that's typically used. So the top would mean it is polar because there is a non-zero dipole that it adds up to something besides 0. The second way of talking about it is that it's non-polar. All right, let's go ahead and pick a few other atoms in this molecule. Let me close this, reopen it. Look at that oxygen in the bottom. See if there's anything missing that you would have to draw in, and then answer that question through the series we did before. If you finish that, try going around the entire molecule and asking that question at multiple different sites. Okay, take a couple more seconds. Did I just change something? Question?
I don't know about, I guess I'm just not like registering it. So every
This is you, right?
no,
Nope.
it's the other. So every time a line changes direction, that's carbon.
Correct, unless it ends in a nitrogen or an oxygen or a chlorine or some other atom. So there's no carbon here, there's a carbon here, there's a carbon right there.
Okay.
All right. That's not what I wanted. This one. Okay. So can someone talk me through the process we went through here, including maybe what's missing, what we had to add, and then how we decide whether it's polar or nonpolar? Okay, so two lone pairs. One thing you're going to find is if you're drawing a lot of Lewis structures, you're very frequently going to find an oxygen with 2 bonds and 2 lone pairs, especially if there's no charge on it. So we can go ahead and draw 2 lone pairs. How many lone pairs does nitrogen usually have? Nitrogen usually has 1 lone pair and 3 bonds. The more frequently you draw Lewis structures, the more you're going to be able to save yourself time and see those trends and be able to write things down. Okay? So then if we have 2 lone pairs there, what are the next questions we ask there? Okay. Sentences?
Oh, okay,
So you have to see if there are polar bonds around that atom. Okay? So we have carbon to oxygen, carbon to oxygen. Are those polar? Yes. They have an electroactivity distance of, I think, 0.9, something like that? 1. Okay. So we put them in that category of polar. Great. So now, what do? We didn't have to do anything for the last one. So what do we do? Okay, not so quick. We can't just jump ahead and say, yes, there's polarity because we have 2 polar bonds. Remember an example we did yesterday was carbon dioxide? Are there polar bonds in carbon dioxide? Carbon oxygen, right? We just said that's polar. So these are both polar, but the molecule is non-polar. Why?
They cancel out the vectors.
So because of the molecular geometry, those cancel each other out. So we can't just say there's polar bonds, so it's polar. That's too simple. So we have to do the same thing here. So now we have to go to oxygen. We have to say, what's the steric number of oxygen there? So our steric number is 4. What's the AXE? AX2E2. What's the electron pair geometry? And then the molecular shape, based on a steric number of 4, AXE of 2, molecular shape is bent, which is very different from the linear CO2, where they cancel each other out. So we don't actually even, if you want to draw out the vectors, you can, that's fine. But for me, I know that the reason it's drawn this way in the molecule is because it's a bent molecular shape. No matter how big those 2 dipoles are, if they're considered polar, there's no way they're going to cancel each other out. Because they're both pulling electrons in the direction of oxygen. They're not pulling in exactly opposite directions. So I'm going to go ahead and say that yes, there's a net dipole. That is, there's polarity around that atom in this molecule. Do you think that's true around most oxygens? Talk to your neighbor. Do you think that's going to be true around most oxygens? Okay, so what do you think? Thumbs up, that's going to be true around most oxygens. Thumbs down, no, that's not a trend. Okay, I see a number of thumbs up. Does someone want to explain why? Very likely we're going to find oxygens in polar regions of molecules, or they make polar regions of molecules. Why? Matthew.
Oxygen usually has 2 bonds and 2 lone pairs, and therefore, and it's not the bond things that are close to its electronegativity.
Because it is so electronegative. So it's very rare. I think I heard Josh say something. When is it bond with something that's similar electronegativity?
O2.
Yeah.
Super common.
O2 is very common molecule, but it's not necessarily how oxygen is found in multiple molecules. So I completely agree that if you find anything bonded to itself, it's nonpolar. Ozone is another example. O3. 3 oxygens bonded together. There's no difference in electronegativity. It's going to be nonpolar. The only thing that's more electronegative than oxygen is fluorine. So unless you see an OF, which sometimes Gen Chem ACS exams will throw at you, even though you never see them in real life, you would know that there's a difference in electronegativity there, and that fluorine is more electronegative. Okay, so the 2 ways that we normally find oxygen are, like we see it here with bent electron pair geometry, 2 lone pairs, 2 bonding groups. The other way we normally see it is a double bond between, between carbon and oxygen. This is one of the most common ways that we see oxygen. 2 lone pairs, double bond. Is there anything to say that's nonpolar? There's 1 polar bond. Is there anything that counteracts the polarity of that bond? Oops. There's only 1 bond, so that's always going to be polar as well. So general trends, that's what I want you thinking about as you're studying all this. Think about the same thing for nitrogen. Think about the same thing for other atoms we typically run across, carbons and hydrogens, okay? Bonding patterns that we see. Let's do the last one before we jump into hybridization. Think about that nitrogen, part of the amide. I'm going to give you guys up to 60 seconds on this. When the clock hits 60, we're going to talk through it. Twenty more seconds. All right, closing out. All right, can I have someone efficiently walk me through those steps? Can I get a new volunteer? New voice, new voice. Trey, would you like to volunteer?
So, as previously discussed, due to that, it's going to be tetrahedral.
Tetrahedral what? Electron pair geometry is tetrahedral. Molecular shape is?
Oh, that's a trigonal
Okay, so before we did all of that, I think after the lone pair, there was one step that you did and you kind of skipped over, and then you mentioned at the end. Are there any polar bonds? Yes. Okay. Nitrogen, hydrogen is fairly polar. Carbon and nitrogen is somewhat polar. They're all considered to be polar covalent bonds. So if you do that step first, you can save yourself the time of figuring out the electron pair geometry, molecular shape, all that stuff, because they're irrelevant. If you don't have any polar bonds, those don't matter. There's still going to be no polarity. Okay? So with all that description in mind, you can kind of picture a trigonal pyramidal. All those have dipoles that are pointing up. The NH dipole is going to be more significant than the carbon-nitrogen because there's a bigger difference in electronegativity. Either way, they still add up to non-zero. So I agree that this is a polar portion of the molecule. And notice that not only is it polar around that nitrogen, it's polar around the oxygen and around the carbon. So this is a fairly polar part of the molecule. That part of the molecule helps it dissolve, and when they're all connected like that, it's called an amide. You guys have probably heard that in your biology classes. It's part of protein backbones. They have an amide where you have a nitrogen connected to carbon, connected to a double bonded oxygen.
I just want to double check. It seems like it's random and pretty common that if it contains a lone pair, it seems to usually be.
If it contains a lone pair and there are polar bonds.
Okay.
Yes.
Yeah.
Because the lone pair typically makes the geometry not symmetrical, and there needs to be symmetry for the dipoles to cancel out. Great question. Great observation. All right. So our goals for the rest of class are to be able to have you explain why it is that hybridization. By the way, practicing that, do you guys have a good idea of how to practice what we just did? Google your most interesting pharmaceutical compound, and then go through the molecule and pick out different atoms and decide what it is. Do it in a group so that you can check each other. If you want to bring those to office hours, that's fine. I only have one more this week, and that's Friday. If you happen to drop by my office and I'm there, that's good. If you have a few people that want to get together and make a time to meet with me, that's fine as well. Send me an email. I'd be happy to do that. Okay, so this is the last chunk of material that's on the exam is hybridization. Friday, we're going to spend some time in balancing equations, which will apply somewhat to lab this week and the following weeks. So I need you to be able to explain why it is that we have to hybridize atoms, and then predict the hybridization based on steric number. So once again, we're going to go around the molecule. Every atom, we should be able to pick out what the hybridization state is of each individual atom. We can then look at molecular shape, steric number, electron pair geometry, relate all that back, and be able to go back and forth between these. And then not all orbitals get hybridized, as you might have seen in the pre-class work. So we need to be able to identify which ones are not hybridized and why those are not hybridized, what happens to those. I did want to make 2 notes on the exam. The one thing you're not allowed to put on the note card for your exam 2 is the thing you need to memorize, polyatomic ions. So if I give you the name of a polyatomic ion, you need to be able to know the formula for that, and then be able to draw it. So a great way to practice that, remember, is to go ahead and look at all the polyatomic ions and draw their Lewis structures. Gives you some practice working with it. On the exam, for parts of the exam where you do need the Lewis structure, or the polyatomic ion to draw the Lewis structure, I promised you that I would test you on that, so practicing that's a good way to do it. If you absolutely blank and you can't remember the polyatomic ion, you can buy that for a certain number of points, so it doesn't ruin your ability to do the rest of the question. Okay? And the second thing is the chemistry department, as you might have heard, is really not a fan of graphing calculators because you can program stuff in like polyatomic ions, which I think is not worth the risk if you get caught looking up stuff like that. But I would like to try for the next exam to not have you bring in your own graphing calculators. The STEM Education Center that I work in has a number of them. I don't know the number. I'm going to find that out today. And so the idea is, I don't really think there's that much calculation on this exam. I don't actually know if is there any calculation on this exam?
Why don't you let me take a look?
So if you would like to use a graphing calculator, what I'm going to do is I'm going to try to borrow as many as I can. I'll tell you in class on Friday how many that is. And then if you have an on graphing calculator you're comfortable with, please bring that. If not, then I will have them to borrow.
Okay, so how many giant molecules are on this disk?
I think I have 2 or 3 larger molecules that you need to be able to do this on. All right, let's do some thought exercise. Let's think about hopefully something that's been bothering you for the last 3 weeks.
Sigma bonds.
Remember we were describing the position of an atom in quantum. Think about what I was really adamant about, how we could describe the position, and then think about how we're describing it in Lewis structures. Talk to your neighbor and think about the similarities and the differences between the 2 ways that we are describing electrons. Alright, so what's the biggest take-home from quantum for how we describe the position of an electron? So our biggest take-home from that. You hear from some different voices? Go ahead, Kayla. Do you want to pass, or did you change your mind? Okay, Ruby?
They act as waves, and you don't know the exact location.
We can't know the exact location, right? There's a probability distribution. If we ask, is the electron here, what is the probability we can find it? That's all we can ask. We can't say it's here. All right, let's contrast that with Lewis structures. How do we describe electron position in Lewis structures?
They're there. Count. Tell you where it is.
They're there, we can count them?
Yep.
What do they look like?
Dots.
Has this been bugging anyone yet?
Yeah.
Okay, hopefully you say yes. It makes me very happy to hear a couple of yeses. All right, so these are two things that don't match, right? We can't know where they are. We can only know the probability. And then here's a dot. This is where the electron is. And they repel each other because they're in these locations. So we need to talk about hybridization in order to understand how that all fits together. So we can't predictably locate them for quantum. They are not dots. They are not Bohr's model. We can assign their quantum functions. But then we start talking about bonding requires an electron from each atom. We put them together. And so this idea of what we actually observe, Vesper, you guys saw in your simulation that you did, that those electrons are mostly located between two atoms. Does that relate to any of the orbitals we talked about? Think about a carbon, a tetrahedral carbon. Right, 4 domains, tetrahedral molecular shape. Does that look like an s orbital? Does it look like a p orbital? Remember, p orbitals are 90 degrees to each other. There's 3 of them. That doesn't come out to tetrahedral. So how we basically let the observed findings match with quantum is this idea of valence bond theory. Once again, Linus Pauling scale of electronegativity. This guy was involved in a lot in the early days of discovering what it is that atoms are, how they interact with each other. So the idea is, if you have a bond, it's really simple to think about 2 hydrogens. You have 1 electron and 1 s for each. When they overlap, you end up with a bond where those electrons are shared. The density actually moves from more spherical to more between the 2 nucleuses. That's called a sigma bond. That's when 1 electron from each atom is shared. Most of the density is between the 2 nuclei. Okay, that's easy. That's cool. But once we start talking about carbon, it becomes more complex. So let's go back and let's think about the quantum description for a carbon atom. What orbitals have electrons in them, and how many electrons do they have in them for carbon? In other words, what's the electron configuration for carbon? Can I hear from a new voice? Bria?
1s2, 2s2, then 2p2.
Okay, so if we think about the valence electrons, that's 2s2, 2p2. So we have 2 electrons in 2s, 2 electrons in 2p. How many electrons do we need for a bond again? If carbon is to make a bond, how many electrons of carbon are we going to use?
4.
For each bond?
Oh, 1.
1 electron. So looking at this, how many bonds can carbon make?
4.
Well, these are already paired up. So there's only 2 unpaired electrons that we can actually use for bonding. Now, that doesn't make sense. Okay, so we could put some energy in, form of light or something else. We could promote one of these electrons up, and then we have 4 unpaired electrons. Okay, that helps a little bit. But this is the shape of all of those. Right? 2s is the green sphere. 2p are the px, py, and pz. Those are all perpendicular to each other. Does that look like a carbon that's tetrahedral? Can you see the connection there at all?
It looks like it's too many. I thought it was just
Too many!
Oh.
They're not in the 4 directions that are most stable. So, if we have promotion of the 2s electron up to 2p, it's the first thing we need to do. And then somehow we need to take those 4 orbitals and make some average of all of them. That's what hybridization is. if we take an S, so if we're looking over here, we're going to ignore the shell. We're just going to talk about what subshells they are. So we have S, P, P, and P. We're going to combine all 4 of those, and we're going to get a hybrid of all 4 of them. What's the mathematical way to represent S times P times P times P? SP cubed, and for some stupid reason in chemistry we say SP3. I don't know, it's really dumb. So SP3 is saying that we have one NS, doesn't matter what shell it's in, and then 3 P's all combined. So how many total orbitals is that? 4, SPPP, there's 4 of them, and now they're all equal. Mohib?
Wouldn't the first electron that hybridizes be a sigma bond, but then wouldn't the rest of them be pi bonds?
So we'll get to pi bonds in a second. But for right now, we're just looking at if we took all 4 of those orbitals and we combined them and made an average of all of them. Then we'd have 1, 2, 3, 4 orbitals. 1, 2, 3, 4. We still have the same number. It's really important that you guys notice that we're not throwing away orbitals, we're not gaining orbitals, we're not changing the number of them, we're changing the properties, and we're merging them all to be an average. Joey?
So how are you moving it from S to P?
The first step?
Yeah, you just pick it up and put it over there, or?
Yeah, so it's called a promotion. It requires a little input of energy. That's in the energy of bond breaking and bond forming. So we don't need to focus on that right now. But it does require some input of energy. Certain atoms don't need that, and we'll talk about that in a second. And then if we look at what do those sp3 hybridized orbitals look like, because we have 4 of them, then each one of those, the shape of each orbital, if we were to look at if this is the nucleus, each orbital has a giant lobe on one side and then a little lobe on the other side. We can't really see the little lobe on the other side, but if you think about it as a big balloon shape on one side, it starts to become a little easier to see how those domains are going to repel each other. And if we have 4 of these, they're going to end up in tetrahedral electron pair geometry. All right, so let's try, Kiana? The little bulb is called an anti-bonding orbital, and in Orgo you'll spend a lot of time with that, but not in this class. So let's see if we're on the same page. What's a steric number for any atom that has sp3 hybridization? Go ahead and click in your answer. Couple more seconds. Can I hear from Avery? Amber, sorry. Avery's over there.
I said 4.
Why?
Because it's tetrahedral. There's 4 of them.
Great. So most of the class agrees with you. So if we have 1, 2, 3, 4, right? A single S and 3 P that are all merged together, there's 4 orbitals. That means the steric number is 4, which then means that we have 4 orbitals that are all identical, spread out in space is going to be tetrahedral electron pair geometry. I think that's one of the quicker questions. So that's our next clicker question. We don't need to click it in, I think. So if we have that carbon that's sp3 hybridized, that carbon is going to have 4 bonds. They're equally distributed. So the electron pair geometry is tetrahedral. And the molecular shape, carbon having 4 bonds, is going to be the same because there's no lone pairs. So now if we think about methane, CH4, we can start to see where we had the carbon that was sp3 hybridized, each of the individual hydrogens that's not, and we can start to see where there's going to be overlap between each one of those sp3 hybridized orbitals and the hydrogen's 1s orbital. And that space between the two nuclei is where we're going to find a lot of the electron density of those single electrons from each of those atoms that's being shared in order to form the bond. Let's try this with a more complicated or a different. Think about NH3. Let's think about that nitrogen. You can either go forwards or backwards. So if we talked about nitrogen having 3 bonds and 1 lone pair. Think about what the steric number is. What hybridization would that be? And then how many electrons would be in each of those hybrid orbitals? So take about 1 minute to try to envision what that process would look like for NH3. We just did CH4. Talk to your neighbor, try to think through this. So let's start looking at nitrogen. Where are the valence electrons in nitrogen? What subshells are they in? Moib?
They're in the subshell.
All of the valence electrons are in 2p?
They're spaced out with 1 in each shell of the p orbital, and there's 3 of them.
Okay, but how many valence electrons does nitrogen have? 5.
2s and 2p.
So there's 2 electrons in 2s, 3 electrons that you're talking about in 2p. We need to keep in mind all the valence electrons when we're talking about hybridization. Okay? So now we have 3 unpaired electrons, which is great for making our 3 bonds, but we know that it's not going to be perpendicular to each other in the p orbitals. So what do? How many of those do we hybridize?
1.
So what's our steric number for NH3?
4.
4. So how many orbitals do we have to hybridize? 4. When we hybridize all 4, we get 4 hybrid orbitals that are all equal. So in this case, we have to hybridize all 4 of them. We're going to end up with sp3, 4 hybrid orbitals. Let's think about where the electrons go in those. We have 5 electrons, we have 4 hybridized orbitals. One of them has to be paired, right? Does anyone see our lone pair yet?
Yeah.
Where?
It's in the first one, isn't it?
So maybe it's a little bit difficult to see on the screen. But because we have 5 electrons and only 4 orbitals, we have to pair up the electrons in 1. That means one of our tetrahedral domains now has a lone pair in it. Does that sound like what you guys have seen with NH3?
Yes.
So the steric number is 4. Of those 4, 1 is non-bonding, lone pair. 3 are bonding. Lone pair, bonding, bonding, bonding. All 4 are going to be equally distributed in space. So if then we think about bonding that, we're going to make our 3 bonds. So if we combine them together, whoa, that's not what I wanted to show. Go back. Here's our nitrogen, sp3 hybridized, 1, 2, 3, 4 identical orbitals. One of them has a lone pair in it. The others each have 1 unpaired electron that they can then share with another atom to form a bond. So then what if we were to do this for oxygen and water? What would that process look like? Take about 45 seconds. Think through the steps for oxygen and water. What's the steric number? You can determine how many hybridized orbitals you would need, and then how many electrons would be in each of those hybridized orbitals. All right, let's have a show of fingers. What's the steric number around oxygen in water? Show how many it is. 4. So how many hybridized orbitals do we need in oxygen? 4, because they're all equal domains. It's tetrahedral electron pair geometry. So if we do that, we hybridize all 4 orbitals, but now we have 6 electrons to put into those 4 orbitals. How many lone pairs do we have? We end up with 2 lone pairs because 6 electrons don't fit into 4 orbitals. We have 2 that are unpaired that can now form bonds with other things. All right, so we've got 3 minutes left. Let's talk about so the sigma bond that we've been talking about is specifically between typically a hybridized orbital and another hybridized orbital. It can also be an unhybridized hydrogen atom. There's also pi bonds, though. So let's think about if our steric number is not 4. What's the steric number in carbon for formaldehyde up there?
3.
There are 3 domains. All 3 are bonding. The steric number is 3. So how many of these orbitals are we going to want to hybridize? 3. All right, let's promote first. We didn't do that step in the drawing. We would promote an electron first, and then we're going to hybridize. So promotion and then hybridizing 3 of those orbitals. We always start with the lowest energy ones first. So it's always going to be S. We're not going to do 3 P's and hybridize those. So if that's the case, S, P, and P, what's that called?
P2.
And how many electrons are we going to put in those?
1 in each thing.
1 in each sounds good. What's missing, though? Mohit?
The other P or if you put all those in P, the other one S orbital or 1 P orbital.
So we only hybridized 3 of the 4 orbitals,
Yeah.
and we left 1 of the P's. Granted, we promoted and we didn't show that step in this diagram. I try to show that afterwards. So that means that we have 4 electrons, 1 in each of these 4. We took 3 of the orbitals and hybridized them. Got 3 that are sp2. We have 1 left over. What do we do with that leftover p orbital? Why is it there? How many sigma bonds can we make right now? That carbon can make 1, 2, 3 sigma bonds. But if we look at that molecule up there, it also has a double bond, or a pi bond. And so if we look at the same process for that oxygen at the top, what's the steric number of that oxygen? How many lone pairs are on that oxygen?
2.
2 lone pairs, 1 bonding domain, steric number 3. What's its hybridization? sp2. That means it also has 1 p orbital that has a free electron in it. And those are what we can use in order to form a double bond. So here's our carbon, here's our oxygen, sp3 hybridized orbitals, and that p is left over that has an electron in it. Here's the one takeaway. As you're walking out the class thinking about this, a double bond actually looks more like a triple bond. Sigma bond is between the 2 nuclei. A double bond, one double bond, it's called a pi bond, is both of the p orbitals, the lobes of the p orbitals are connected. So that means that that is 1 pi bond. So this is a double bond shown on the right. The pi bond is above and below, sigma bond is in the middle. Think about what a triple bond would look like. We'll talk about that at the beginning of class on Friday.
You said this is going to be on the test.
So you need to be able to look at an atom and say, what's the hybridization of that atom? Or if I know the steric number, what's the hybridization? Or if I know the hybridization, what's the steric number? To be able to use it like that.
Okay, so it's all correlating steric numbers.
NAXE, all those things kind of fit together.